So let's go through the derivation of the so-called shallow water equations, which are a classical set of equations derived under special conditions in the atmosphere and ocean, and have been very instructive in deriving some of the tropical wave solutions for the ocean and the atmosphere. There are many details, assumptions involved, so please read the book to make sure that I didn't miss anything. We start with the simple vertical cross section showing a part of the ocean. So we're doing, because it's shallow water equation, we start with the ocean, but the atmosphere also has a so-called shallow water equation because it mainly corresponds to the assumptions made, where the average depth of layer thickness is h. You can see minus h is here and 0 is here, and the ocean surface undulates on top of that with the sea surface height with respect to that mean sea level 0 by eta, and then the ocean has a bottom which variation is represented by eta b, eta bottom, and the local layer thickness h obviously is a combination of the average thickness h plus eta and minus eta b. As you can imagine, z bottom height is minus h plus eta b, so if eta is below the h, then it is negative, so z is deeper. If the bottom sticks up, then it's positive, so z decreases, and the surface height eta here. So the local layer thickness is h plus eta minus eta b. So that's just a combination of all these three. So just keep that picture in mind so that you know what we mean when we say z and eta b and capital H and small h and so on and so forth. So z equal to eta at the surface, z equal to minus h plus eta b at the water interface at the bottom, and the average thickness h is the average thickness of the water layer, water column, plus the surface deviation or surface height minus the deviation of the bottom from the average thickness. And we assume that this is a shallow water, which means the vertical scale is much smaller than the horizontal scale, so that we can neglect the vertical acceleration term dw dt, where this is still the material derivative, so it is partial w partial t plus u dw dx plus v dw dy plus w dw dz and so on. So that ends up making this equation dw dt equal to minus 1 over rho dp dz minus g that we derived before, to go to the hydrostatic relation dp dz equal to minus rho g. This simplifies life in many ways once we ignore the vertical acceleration term. Vertical velocities need not be zero. There are special ways in which W acts that we will see in a minute. So pressure P at any Z here can be written in terms of the water column above, because in the hydrostatic balance, pressure at any depth is equal to the weight of the water above and the additional pressure due to the atmosphere above. So we can use that to say that P at Z is P at the surface at eta plus P at Z minus P eta. So essentially, what is the pressure from the free surface to that depth plus what is the atmospheric pressure above. Typically we ignore the spatial variations of the atmospheric pressure, and then life simplifies a bit more, as we will see. So you can write this as P eta plus dp dz, where we are integrating this equation to get the mass above, going from the surface, free surface, down to that depth z. So use the figure just to make sure you know where you are. Then this can be simplified as p eta plus rho g times eta minus g. So essentially, for a unit area, the weight of the liquid above the depth z is just rho times g times eta minus z. So that's the depth of the water column from the free surface to the depth z. So this is a simple expression that says by hydrostatic pressure, P at any depth z is just the weight of the water column above, which is rho g times eta minus z, plus the atmospheric pressure, which is pressure at eta, the free surface. So with that, we can write dp dx equal to rho g d eta dx, and we can write dp dy as rho g d eta dy, because within the any column, the pressure variation in the vertical are constant. Okay, so you can, oops, where am I going with that? Did I do the right thing? Yes, okay, so you can differentiate this to get dp dx and dp dy, and that's what it gives you in terms of the sea surface height. So the gradients of the sea surface height correspond to the horizontal pressure gradients under hydrostatic balance when we have the special situation we've been talking about. So obviously the pressure gradient within the layer in the hydrostatic equilibrium are independent of z, because dp dz is rho g, and if rho is constant, that is a constant. Due to this important fact, the horizontal components of the velocity u and v are constant with height for all times if you start with a case where u and v are independent of height. So if you have initially no vertical shear, then you will have no shear through the flow period, because hydrostatic balance requires that this is not possible. It just turns out that in this special case, the columns move as rigid bodies. You cannot have shear within them. Okay, provided this is the case. Provided this case, the friction forces due to shear stress vanish, because you cannot have shear stress within the fluid or at the surface, and horizontal component of the equation of motion 612, which is this. We wrote du dt, dv dt, dw dt in terms of pressure gradients, the shears, and the Coriolis. In the vertical, we had this, which became our hydrostatic. So the shear terms are gone, so we have the horizontal, the zonal acceleration term, material derivative as partial plus the advection terms, and the pressure gradient terms in terms of the sea level, and the Coriolis similarly in the meridional direction. And we need the continuity equation, because you have three unknowns u, v, and eta. So the eta equation comes from integrating the non-divergence or continuity equation for constant density, that was just divergence u equal to 0. So du dx dv dy plus dw dz can be integrated from the bottom of the water column, which is minus h plus eta b, as you remember, to the free surface eta, and that can be written as minus h plus eta b to eta du dx. So we can separate these out, and that has to equal 0, because that is our continuity equation. And we have already said that u and v are constant, and w is not set to 0 here. dw dt is 0, but not necessarily w. So we integrate these. So limits of integration z1 equal to minus h plus eta b. Minus h is the average depth, and you have the bottom varying on top of that. And any z2, you can go up to the surface sea level, which is z1 plus h, which is the water thickness at any location. So they are functions of x and y. So z1 is z1 x and y, because eta b is a function of x and y. The bottom topography varies, and sea level is a function of x, y, and t. So we have z2 equal to z1 x, y plus h, the local thickness, as a function of time and x and y. Okay, so using the Leibniz integral rule, which is the rule for differentiation of a definite integral that we are doing here, and noting that velocities u and v are constant for this case, minus h plus eta b to eta du dx times dz can be written as d dx. So we can pull out d dx because we are integrating in dz here. Minus h plus eta b to eta u dz, and we can write this also as minus u d eta dx. So the contribution of the sea level gradient or pressure gradient, and contribution of the variation in the bottom topography, which also introduces pressure gradient. Okay, so that can be written as d dx of u times h plus eta minus eta b minus u d eta dx plus u eta b, because here u, we can use the relation here of the h to be h plus eta minus eta b. Okay, so that is basically h. So this is d. We are basically integrating this. U is constant, so we are taking integral of dz as h plus eta minus eta b, h plus eta minus eta b, but this term is h, so we end up with a flux d uh dx minus du d minus u d eta dx plus u d eta b dx. Okay, just look at the book again and look at this podcast again to make sure you are following. Looks like a lot of equations, but actually it's fairly straightforward. They are all parallel to each other. So similarly, for the meridional gradient of meridional velocity dv dy dz in the continuity equation, we end up with d dy of vh, meridional flux with the local height, minus dv d eta dy, pressure gradient or sea level gradient in the meridional direction, plus v d eta b dy due to the bottom pressure gradient. And similarly for w, again w is not necessarily 0, so that gives us w at eta minus w at the bottom, so minus h plus eta b. Okay, so if there is no exchange of water at the top, and of course if the bottom is rigid and no water can come out or go in, then they can become 0. So it depends on how the boundary conditions are set. So looking at our continuity equation again, we can write this as partial uh partial x minus u d eta dx plus u d eta b dx, plus similar term for meridional, and the vertical term w eta minus w minus h plus eta b equal to 0. This is w at the sea level and w at the bottom. Okay, so the difference between the vertical velocity at the surface, if you have exchange, and the vertical velocity at the bottom corresponds to the change in height per unit time of the water column between minus h plus beta eta b at the bottom and eta at the top, therefore to the material derivative with respect to the horizontal motion. So even though dw dt is 0, when you have horizontal motion, so flux is in the meridional zonal direction, the height of the water column adjusts because the divergence has to go to 0. So between corresponds to the change in height per unit time of the water column between minus h plus eta b and eta, and therefore to the material derivative with respect to the horizontal motion of the column height h t xy. So h is changing in time and space, so that is written again as h, the average depth, plus eta times txy, sea level variations in x, y, and t, minus eta b xy. The bottom is not changing in time, so that's just function of x and y. So in this case we can write the difference in w at eta and w at the bottom to be dh dt, the material derivative, which of course is dh dt plus u dh dx plus v dh dy, which again we can use the relation to write in terms of d eta dt, time variations of the sea level, plus u d eta dx, how the sea level is being affected in zonal and meridional, and how the bottom pressure is introducing pressure gradients and contributions to the height change in the material derivative sense. So that can be put back into our 618 to get a simple relation d eta dt plus u plus duh partial uh dx plus partial vh dy equal to 0. Okay, so we have now derived the continuity equation in terms of the time variations of the sea level and horizontal fluxes with local height of the local thickness of the water column at any depth h. Okay, so because h is h plus eta minus eta b, where h as well as eta b are time independent, so even though sea level is varying and bottom is varying, this average depth remains constant because that's the time average or a column we are talking about. So that gives us dh dt plus partial uh partial x plus partial vh partial y equal to 0, and we have now the whole set of shallow water equations with all these special assumptions. Dut plus u du dx plus v dv dy equal to minus g d eta dx plus fv. So similar equation in the meridional direction, and the continuity equation with h thickness being given by this. And under special cases, this equation system becomes simple for the case of a non-rotating Earth, f equal to 0. So this goes to 0. Then you can do some manipulation. So assume that it's a flat bottom, velocities are small, and elevation is much smaller than h, as well as the spatial derivatives of uv and so eta is much less than h, as well as small space derivatives of uv and h. In this case, the Coriolis terms vanish and the nonlinear terms are negligible, so you end up with these equations. The zonal and meridional accelerations are directly related to the pressure gradients as represented by the sea level gradient, and the continuity equation is going to reflect the horizontal divergence into the sea level variability in time. So we can take the time derivative of the continuity equation here and manipulate these two equations by taking the space derivative d dx of 6.21a and d dy of 6.21b and write a single equation, del square eta del t squared equal to gh grad square eta. So this is one equation now in terms of sea level when you have a flat bottom, Coriolis is 0. This is similar to our wave equation we looked at in chapter 3. This was in space and this is in time. So this solution to this can be derived easily as dispersion-free harmonic waves with phase speed of square root gh, which we will come back to and look at as gravity waves in the case of Earth system, especially Kelvin waves and so on. But you can also add Coriolis and have some simplifications in terms of the nonlinear terms in the shallow water equations and derive Kelvin waves, Rossby waves, and so on, which we will look at later on. So in the next podcast, we'll move on to the numerical solutions and look at these equations again. So this is a slightly longish podcast, but I wanted to keep all the derivation into one podcast. But please make sure you read the book and make sure you understand all the derivation we made with all the assumptions along the way. Hydrostatic balance being the most important one, and then the rest that followed. Okay.